Okay, so this next section deals with what we call the determinant of the matrix. And basically the determinant is just a number associated with our matrix. And it's a very, very important number because it does some interesting things when we find the determinant of a matrix. And it's pretty simple. If I have a 2 by 2 matrix, then D is the determinant of the matrix, which is kind of denoted by, it's almost like an absolute value sign, as you can see. And it is the diagonals multiplied together minus the off diagonals multiplied together. So just make sure you're going the way you read first, left to right, then go backwards. So AD minus BC, that's the determinant, and it's that simple. So let's do some practice. Let's find the determinant of these two guys. So again, remember the determinant is AD minus BC. So the determinant of this matrix is, we go 1 times -4 is -4 minus 3 times 2, which is 6. So -4 minus 6 is -10. That's the determinant of that matrix. This one is 12. 3 times 4 minus 5 times -2, which is -10. This one is 22. So here's that is exactly how you do it. It's very, very simple to find the determinant of a 2 by 2 matrix. So one of the things that we can do, and the reason we do this, is because we can use this thing called Kramer's rule, which is kind of a really cool result. And what it does is, if I have a system of equations, which this is, I think, the last way we're going to talk about how to solve a system of equations. I think we've done it about 12 ways now. AX plus BY equals U, CX plus DY equals W. So then what we're going to do is, on the bottom, we need the determinant of the regular coefficient matrix on the bottom. Now on the top, we replace the coefficients of the variable we want with the constants. So in this case, I'm replacing the coefficients of the variable I want with the constants over here. And so what that does is that allows me to actually solve this equation. And I do the same thing for y. So I replace the coefficients of the variable I want. Here I want x. And then I take the determinant of this matrix and put that on top. It's really cool. And of course it says, provided that my determinant of my coefficient matrix is not 0. If it is, then the system does not have a unique solution. Okay, so let's see this thing in action. So I want to use Cramer's rule to solve this system of equations. So the first thing we need is the coefficient matrix. Oops, come on. So the coefficient matrix is just 3, 2, -1, 5. So now we need the determinant of this. The determinant is 15 minus -1 times 2 is -2. So the determinant is 17. So now we need the coefficient matrix with the x's replaced. So, coefficient matrix with x replaced. Okay, so we're going to instead put 7, 9 here, 2, 5. So now what is my determinant of x? So 7 times 5 is 35. 9 times 2 is 18. Looks like we get 17 again. That's nice. That's going to be good later, right? Let's find my coefficient matrix with the y's replaced. And not really the y's, the coefficients of x, the coefficients of y's. So let's look at that. So we keep our 3, -1, oops, sorry, and we replace 2 and 5 with the constants 7 and 9. So my determinant of the y matrix is 3 times 9, which is 27, minus -1 times 7, which is -7. So that's 27 plus 7, which is 34. So now, in order to use Kramer's rule, x is the determinant of the x over d, and y is the determinant of y over d. So this is 17 over 17, which is 1. This is 34 over 17, which is 2. And it's kind of magic, and that's one of the things I like about it, is it's kind of magical that it does that. So we can check these answers real quick. So let's check. I'm going to check using a different color here. Red. All right. So let's check using red. And 3 times 1 plus 2 times 2 equals 7. 3 plus 4 is 7, yes. And the second equation, -1 plus 5 times 2 is 9. -1 plus 10 is 9. Check. So my ordered pair is, the answer to this question, 1, 2. Is my ordered pair that makes this system true. Seems like a long thing, but in some ways it's just kind of really cool that there's another way to do it that might be a little simpler to you. So let's do another one. Let's use Kramer's rule to solve this one. So first of all, we want to find the determinant of the coefficient matrix. Remember, for determinants, we can use this absolute value sign. So that's 14 minus 15. So 2 times 7 minus 3 times 5 is -1. So now let's find the x determinant. So we replace my x's with 9 and 13. Okay. We go back. 9 times 7 is 63. Minus 5 times 13, which is 65, and I get -2. And then let's get dy. So we're going to replace the y ones now. So that's 26 minus 3 times 9 is 27, so that's -1. So now we know that x is dx over d. So it's -2 over -1, which is now a +2. And y is dy over d, which is -1 over -1, which is 1. Very similar to the last one. So let's see if we're right. Let's check this and see if we're right. Okay. So 2 times 2 plus 5 times 1 is 9. 4 times 5 is 9, yes. So 3 times 2 plus 7 times 1 is 13. 6 plus 7 is 13, yes. So the ordered pair that solves this problem is 2, 1. In some ways, it is faster. It's one of the fastest ways to solve a 2 by 2 because you can easily find determinants of 2 by 2 matrices. Now, let's talk about determinants of a 3 by 3. This is a little bit more difficult. Now, I chose the A column to work on in the interest of simplicity, but any column or row can do this. And a lot of times what I will do is I will pick something with a 0 in it because it makes my life easier. So then basically what we do is we pick a column or row and we say, okay, this is going to be my main column. And then the determinant is found by taking this number, A, times the determinant of the 2 by 2 matrix that's left by crossing out the row and column that it's in. So you can see this becomes B2, B3, C2, C3. Okay, then, so that's the first part. Then we subtract the second one, and we always add up its row and column to see if we add or subtract. If we add up the row, so this is in the first row, first column, 1 plus 1 is 2, it's even, so it's positive. This is in the second row, first column, 3, odd, negative. So we subtract EA2. We cross out its row and column, and the resulting matrix B1, C1, B3, C3 is what we take our determinant of. And finally, A3, which is in row 3, column 1, is 4, so it's even, so it's positive. And we cross out A3, we cross out A3, and we're left with this matrix, B1, C1, B2, C2. Now, I'm going to do one of these, but I want you guys to know that we are also going to look at how to do this on the calculator. So, now there's a nice little 0 in here, and that would definitely be one way to do it. That's not the way that I did it here, just because I wanted to just keep this consistent with the example that we just did. So we start, and we're going to use 1. So we find 1 times the determinant, 0, 1, 2, 1. And that's going to be 0 times 1 is 0, minus 2 times 1 is 2. So that's going to be negative 2. So that's the first number. So for the third one, this is also the number, oh, that's the number negative 1. Isn't it? Is it? Yes. So that's negative 1. But remember, this has to be negative. So it's negative 1 times the determinant, 2, negative 3, 2, 1. So we have 1 times the determinant, 2, negative 3, 2, 1. And that is 2 minus 2 times negative 3 is negative 6. So that becomes a positive, and this is 8. So for the third minor, it's going to be negative 2 times the determinant, 2, negative 3, 0, 1. So let's see what that is. Negative 2 times, let's see, 2 times 1 is 2, minus 0 times negative 3 is 0. So negative 2 times 2 is negative 4. So now we add, well, I already did this, I made it negative. Already. So let's take these. So I have negative 2 plus 8 minus 4. And let's see what I have. 6 minus 4 is 2. So that's the determinant of this 3 by 3 matrix right here. The determinant is 2. So that's kind of a pain to do. So what we normally do in this case is we, of course, use our calculator. So what we can do is, let's take a look at this. Let's go back to this guy. And let's check our answer. So remember, to do a matrix, we're going to go second matrix. We want to edit. We want to enter matrix A, which is a 3 by 3, and hit 3, enter, 3, enter. 1, 2, negative 3, negative 1, 0, 1, negative 2, 2, 1. Okay, so there's the matrix that I just found the determinant of. Now, I'm just going to quit out of this, go back to matrix, go to math. Determinant is number 1, and I want the determinant matrix A, so I'm going to second matrix, pick up A by hitting that one, hit enter. 2, we were right. It's always nice to get the right answer. Okay, come on. There we go. All right. So we did that. And A, I didn't even add the right parenthesis. That's not necessary. And just pressed enter. Now what's really cool is if you have a matrix in Excel, you can actually use this function called mdeterm. I'm not going to show that right now. But it's just a nice thing to know that you can do that also in Excel. Okay, let's talk a little bit about Kramer's rule when the determinant is 0. Now, what's interesting about the determinant of a coefficient matrix, any coefficient matrix, if it is 0, then it means that the system is either inconsistent or contains dependent equations, which essentially means that there's not a unique solution. Which also means that the matrix is what we call singular and not invertible. Because remember, we talked about how some matrices were invertible and some were not. So this all comes full circle now because it's a singular matrix. It's not invertible. Its determinant is 0. If it were a coefficient matrix, it doesn't give you a unique solution. So if the determinant is 0 and at least one of the determinants in the numerator is not 0, so if it's not all 0 over 0, there is no solution. Okay. If d equals 0 and all the other determinants d of x and dy are also 0, then they are dependent. You have the infinite many solutions and you have to use row reduction to find the general solution. So that's really important. Remember, I have to have the general solution when you have a dependent system.